Let us look now at the principle of angular impulse and momentum. We've discussed before the principle of linear impulse and momentum. Let's apply the same intuition to the angular momentum. So similarly here, the expression is of the form HO1, which is the angular momentum at state 1, plus the sum of all the moment contribution across delta t is equal to the angular momentum at state 2. And how do we calculate the total sum of moments? Well, the moment is the cross product of r and f, so it's r in magnitude times f in magnitude times sine theta, where theta again here is the angle between the r vector and the f vector. In scalar form, MO is equal to r perpendicular times f, where r perpendicular is the perpendicular distance from O to that vector f. And now if you just look at this expression, I'll just add here on the right the expression of linear impulse and momentum, and you can see the striking similarity. So where we have linear momentum as a term, now we have angular momentum, and where we had sum of forces, we now have sum of moments. So we can see that those two expressions are very, very similar. Similarly, we can talk of conservation of angular momentum, and that is again the case where the middle term just cancels out. So sigma MO dt is actually equal to 0. So let us look at the two cases in which this is true. If I expand sigma MO dt, I can say HO1 plus summation of the cross product RF dt is equal to HO2. So what are the cases in which the cross product RF is actually equal to 0? We have two cases. If f is parallel to the axis of rotation, then the projection of f would be 0, and so r cross f would be 0. Another case is when f is oriented towards the center, and in that case r and f would be collinear. There would either be an angle theta of 0 or 180, and so if you look here at the expression, sine theta would automatically be equal to 0, and so the moment is equal to 0. In this case, we can say HO1 is equal to HO2. So in summary, we can make use of three equations of momentum in the case of 2D rotations. If we split that onto x, y, and z axis, we get mvx1 plus summation of integral fx dt is equal to mvx2, mvy1 plus summation of fy dt is equal to mvy2, and ho1 plus summation of mdt is equal to ho2. So with the principle of linear momentum and angular momentum, we get three scalar equations, so they can solve for up to 3 unknowns. Now, what are the steps to solve problems related to both angular momentum and linear momentum in the case of rotations or curvilinear motion? Well, first we have to select a coordinate system, x, y, and follow a sign convention. We can then draw the free body diagram, and then we apply the three equations for a rotating object. So 2 linear momentum equations and 1 angular momentum equation. And then hopefully with those 3 equations, we'd be able to solve for whatever unknowns we're looking for.